In this video, I want to start talking about coordinate systems. And so we'll first consider one-dimensional coordinate systems. And coordinate systems play a very special role in what we're trying to do here. In fact, we'll also refer to them by a separate name called reference frames. Reference frames or coordinate systems. And what we use them for is they are the tool that allows us to make quantitative measurements of position. And therefore they play a very special role in transferring or changing from sort of a pictorial representation of what we see into something that we can then quantify. So let's take an example. So let's take a very simple example. I'm going to have a table. Yeah, very narrow-legged table. And I'm going to watch a ball roll across the table. And so let's say it started here. 1 second later, it was here. 2 seconds, it was here. In 3 seconds, it was here. 3 seconds after it started. And so you can imagine taking a movie of this or watching it with me. Here's this table, and we had this ball, and we watched it roll across the table. Now, if I wanted to make a quantitative description of that motion, how would I do it? Well, so first, what I'll call this is sort of a pictorial representation. I've drawn sort of a picture of what happened. So if I want to make that quantitative, to do that, I want to add a coordinate system. So a coordinate system has some characteristics. So one-dimensional just has one of them. You have to choose somewhere where it's a zero of your coordinate system. I'm going to choose, let's say, the zero of my coordinate system to be the edge of the table. And I need a direction of positive. Well, I'll just say I will need to identify the positive direction. And this is a measurement of position. So it has some units of position, which I'll call centimeters. And so now I need this coordinate system has some measurements associated with it. And I might find that from the edge of the table, from this coordinate system where the ball was when it started was at 5 centimeters. You know, I didn't set this up very well to be. Let's say this was here's my edge of my table. So I might, given this coordinate system where my zero was at the edge of the table, the ball was at 5 centimeters when it started, and 15 centimeters 1 second later, 25 centimeters 1 second after that, there's 30, then 35 centimeters 3 seconds after that. And so with my coordinate system, I now have a quantitative measurement of position. So a coordinate system or a reference frame is a tool that we take out that we then place on our pictorial representation, our schematic representation that gives us some quantitative measure of what's going on. All right, so I might, if I wanted to look at this in another representation, I could make a tabular representation of what's going on. So at some time, position, given my coordinate system, I have time is equal to 0. I have some 5. This is in centimeters. Times is in seconds. And at 1, it was at 15. At 2, it was 25. At 3, it was 35. There's a tabular representation. And then we can finish this off with a graphical representation. If it's 1, 2, 3, so this is 1, 2, 3, 0. This is in seconds, and this is my position as a function of time in seconds. So if this is, we said 10, 20, 30, so 35, 25, 15, and 5. We said that t is equal to 0 is a position at 5. At 1, it was 15. 2, it was 25. 3, it was at 35. And so I see that this was a straight line. And so this would be a graphical representation. So I'm playing again with the idea of multiple representations for an object, but at this point what we really want to highlight is our use of the coordinate system, which was what we put on the problem to be able to allow us to do quantitative measurements. Okay, let's do another example. Only this time, I want to emphasize that the choice of coordinate system, origin, and direction is entirely up to you and can change how the quantitative measurements we make. All right, so let's find the ground here. I'm going to draw the ground all the way across the screen. And in this case, what I'm going to do is I'm going to drop a ball. And so it's at some height here, and then 1 second later it's dropped a little bit, and then 2 seconds later it's here, and then at 3 seconds later it's almost hit the ground. So this is sort of 4 seconds in time. T is equal to 0, 1, 2, and 3. And this is my pictorial representation of the problem of a ball falling to the ground, and I've sort of drawn it at 4 different points in time. Okay. And so I want to make a quantitative measurement of this, and so I need a coordinate system. So let's make a coordinate system. I'm going to have my origin at the ground. So if this is an x one-dimensional motion, I'm going to call the position x along my one dimension, which means I think I did this in meters. Okay, and so I'm going to call the 0 of my coordinate system to be on the ground, and I'm going to have the positive x direction to be up. And then when I made measurements on this, I found that, let's see, that this was 50, 40, 30, 20, 10. Not exactly evenly spaced, but we'll get the idea. So this was 10, 20, 30, 40, 50. So now with my establishment of the coordinate system, I was then able to make measurements of the position of my object at different points in time. I found the position at 0 was equal to 50 meters. The position at t is equal to 1 was 45 meters. The position at 2 seconds was 30 meters. And the position at 3 seconds was equal to 5 meters. See, I'm just sort of 45, 30, here is 5. And so there's a tabular representation. If I want a, let's see if I can get a little, let me give myself a little extra space. This is x in meters. All right. And so if I want a graphical representation of this, I can do that. So this is now time in seconds. This is now position in meters. So 10, 20, 30, 40, 50. And then 1, 2, 3. So 1, this is 10. I'm not going to put in all the numbers. You get the idea. That's 50 up there. That's 3. All right. So where was this object? I'll do green dots again. At 0, it was at 50. At 1, it was at 45. At 2, it was at 30. And 3, it was at 5. And so the graphical representation of my system looks something like that. Okay, well that's all fine and good. What I'd like to emphasize is that we did not have to put the coordinate system in that way. So let's do another coordinate system. In this case, I'm going to set my 0 of my coordinate system to be at the place where the ball started. So that's going to be my 0 of coordinate system. And I'm going to have then the positive x-axis in meters to be up, and the negative, again, just like before, negative is still down. So, but in this case, I need to, here's where 40 was before. This is -10, -20, -30, -40, and then the ground is at -50. So in this coordinate system, the position of my object at t is equal to 0 is equal to 0. My position at x equals 1 is equal to -5. My position at x equals 2 is -20. See this, right? My position at t is equal to 3 then is equal to -45, and these are all meters. So, if I wanted to graph this, what would it look like? My tabular, as can be seen, is different. So if this is now, I'm going to draw my time up here. This is my 0. This is now negative x-axis. -10, 20, 30, 40, 50. And 1, 2, 3. So here, my particle started out, t is equal to 0, x is equal to 0. Then t is equal to 1 second, it's at -5. 2 seconds, -20. You see these, this is -10, -20, -30, etc. And so then at 3, it's -45, which is down here. So my graphical representation looks like this. Now you might say, look, those curves look very much alike, even though the coordinate system is changed. That's true, but we can change the character of the curve as well with a different coordinate system. Now let's try. I'm going to do one more coordinate system. Now in this case, get myself over here where I have more room. I'm going to keep my 0 here. This is my x equals 0. But in this case, my positive axis is going down. This is my positive x-axis in meters. So in this case, right here is now a +10. This is +20, then +30, +40, and the ground, which ground here, +50. There's no reason that positive has to be up. You can choose the positive to be any direction you want, and you can call it anything you want. In fact, let's not call it positive x this time. Let's call it positive y. This can be the y-axis, and it can be the positive direction can be down. These are all choices that we get to make when we solve problems. And so here now at y is equal to 0, again, the position is y is 0 meters at t is equal to 0. The y coordinate at 1 is now +5. Y at 2 is then +20. And y at 3, I'm running out of space to make my graph here, 45 meters, meters, meters. So what does this look like graphically? Well, again, 1, 2, 3. This is time in seconds. And now we've got 1, 2, 3, 4, 5. This is y in meters. This is 10 through 50. And now at 0, t is equal to 0, y is equal to 0. T is equal to 1, y is equal to 5. T is equal to 2, y is 20. And t is equal to 3, y is +45. So we have a kind of the shape that we had before, but flipped flipped the other direction. And so a coordinate system is a way that we can translate, this way we take a picture of something and make quantitative information from it, and it lets us translate from a pictorial representation to this, I'd call this sort of a schematic representation, to a tabular representation, a graphical representation, eventually a mathematical representation. But to make those quantitative measurements, we need to have a coordinate system. But the important lesson in this last part is that as the problem solver, you get to choose where the zero of the coordinate system is and in what direction positive is. And with great power comes great responsibility. You need to make that choice, make explicitly clear when you are working on a problem where your coordinate system is, where the zero is, and in what direction is positive.